Hello everybody, welcome back. In this video want to discuss with you the next conversation within an integration chapter. So we've been looking at different concepts about integration. We started the conversation where we were finding area under a curve, and that motivated us to basically doing integral to calculate areas. Now, as we talked about in the prior video, there are lots of other applications for integrals. We've just been motivating the conversation using area. Now, every integral that we have computed up to this point, we're using an antiderivative to calculate those integrals. Now, all of the antiderivatives that we've been doing have been relatively simple. Right? And what I mean by that is let's say we integrated x squared plus 1. And for our indefinite integral, no limits of integration, right? We would take the antiderivative of x squared, that was 1/3 x cubed. The antiderivative of 1 was x, and then we had our constant of integration. So in that example, we're using, what we called the power rule. We could have also integrated something like square root of x. And what we would do with an integral like this is we would want to use the power rule as well. So I'd write the radical as a rational exponent. So I'd add 1 to a half, and I'd get 3/2, right? 1.5, and then I multiply by its reciprocal. We might have done something like integral of secant squared of x, and we knew that that was tangent of x, right? Because the derivative of tangent is secant squared. Right? So in all of the problems that we had been doing, we're doing, for the most part, simple, and I hate to say that anything in a calculus course is simple, right? We've been doing relatively straightforward integrals. Probably one of the most difficult integrals we might have done before this section is maybe something like, let me scroll down a little bit more, some of the problems you might have had might have been like 1 plus 3x squared minus, root x, right? All over, let's say, x. So even though I couldn't do the power rule right away, what I would do is simplify that integrand, right? So typically our approach, I am missing a dx here. So pretty much what we would do in this case is a little algebra. We would split each of those terms in the numerator over the denominator. And we would integrate that expression, right? And what this would allow us to do, in essence, is integrate each of those terms separately. So let's see, I'd simplify this and get just x. And then when I divide like bases, I subtract exponents. And I keep getting sloppy. There's a dx in that middle integral, right? So what this would allow me to do is the known, or what I would consider an elementary integral. Right? So we'd have ln of x from this guy. We'd have 3 times 1/2 x squared from this middle integral. And then we would have, so we add 1 to the power and then multiply by its reciprocal. Barring any cleanup, there's the antiderivative. Now this is all work that we've done prior. Now what we're going to look at in this section is where we have integrals that we can't simplify and bring us back to a quote-unquote elementary integral. So in our last video, when we were talking about indefinite integrals, right, this is what I'm referencing in terms of, elementary integrals. These are, sometimes I call this a brute force, right? So these are formulas that we know because we already know derivatives, right? So, this example here, we know the derivative of tangent is secant squared, therefore the integral of secant squared is tangent. So these are, quote-unquote known forms. So what we're going to look at in this section is integrals where we can't exactly match those known forms. Even like that last integral we just did a minute ago. I can't do algebraic simplification to match a known form. So this is typically called, so there are actually a couple different techniques of integration. Usually in a Calculus 2 course, you'll look at other techniques of integration. So the first one in this chapter we look at is what we call the substitution rule, which is sometimes called U-substitution. So I just want to start off and do a couple examples. I'm going to let you try a couple on your own where we practice this technique. So let's see, what do I want to do here? Let's take a look at something like this. So let's say we're going to evaluate the integral of 1 over 2x plus 1. So here's the integral I want to find, I want to evaluate. I want the antiderivative of 1 over 2x plus 1. Now if we scrolled back up to that prior page that we just had, right, we know that the integral of 1 over x is the ln of x plus some constant, right? So we kind of have something similar here, right? Notice we have like 1 over an x thing. So we have 1 over something linear. That's really what this term says here. This is 1 over something linear is going to be logarithmic in form. But the problem is this, this form needs just x, right? And I have more than just x here. So what we're going to do is what we call like a change of variable. This is our U-substitution. So in other words, what would be really cool here is if all of this stuff right here was just x. So what I'm going to do is a substitution, and I'm going to let this new variable u replace that entire denominator. So in other words, I'm going to see if I can switch colors here. So let me come over here. So in other words, what I have is 1 over, and I now have u in the denominator. So I'm in essence matching this integral by doing this change of variable here, right? which is pretty cool, right? However, there's one other piece that we need to connect to. And when we come back to these indefinite integrals, remember that this dx term can symbolize for us that x is the independent variable. So my integrand is in terms of x, and then my integration variable is x. Now when we do this replacement, this substitution, a U-substitution, now my independent variable is x, but I'm supposed to integrate, now my independent variable is u, and I'm supposed to integrate with respect to x. I have a mismatch in variables there. So what I need to do is get the dx in terms of the u variable. Here's how we're going to accomplish that. So let me switch colors again. So what I'm really thinking of with my substitution here is I've made u a function of x. I could think of this as u being a function of x. I'm going to write function notation here. I'm going to say u is a function of x as 2x plus 1. So the way that I'm going to generate the du term that I need here is I'm going to find the derivative of u. I'm going to find u prime. Right? I'm going to take its derivative. So I'm going to find u prime. I'm going to find the derivative of u. So for what we let u equal, what is its derivative? Its derivative is 2. The derivative of 2x is 2. The derivative of 1 is 0. So there is its derivative term. Now the advantage to this is what it's going to allow me to do basically is like another substitution. I'm going to solve for the dx. So I'm going to take the dx term and multiply it to the other side. And then I'm going to isolate the dx. I'm going to divide the 2 over. And this is now going to allow me to replace the dx with this du expression. So I'm going to come back up here on my integral, and I'm going to replace the dx with this expression. So this dx is now 1/2 du. And what we have accomplished at this point is we have converted my original integral, which was all in terms of x's, to an integral all in terms of u's. We've done a change of variable. Now, before I finish off this integral, the advantage to that, the reason we did this is now this integral is 1 over u du, and that's really what we have in this known form. Now remember, the variables in these integrals don't really matter in the sense of what's the antiderivative. So even though this is 1 over x dx, this is 1 over u du. Right? 1 over x dx is ln of x. 1 over u du will be ln of u plus c. Now, I've gotten a little lazy in my conversation, and this 1/2 that I'm circling here, I need to have in front as well. Right? Remember, I'm really taking the 1/2 out as a constant, and I'm evaluating 1 over u. So the integral of 1 over x dx is ln of x. The integral of 1 over u du, integral of 1 over u du is ln of u. So these are the types of problems we're going to see in this section. The original integral that we're giving doesn't match one of our quote-unquote known integrals. So we're going to do a change of variable. When we change the variable, it's going to simplify, if you will. Right? It's going to, I don't like to use the word reduce, right? But it's going to simplify the original integral that we have in terms of a new variable. And the sole purpose of doing that simplification is to get it to match a known integral that we have in that table that we looked at just a minute ago. All right? This is the general concept, doing a change of variable here. This section is typically called the substitution rule, or sometimes called U-substitution. Now there's two things I want to discuss a little bit deeper here. One of them is, how do I know what to let u equal? How did I know I needed to let u equal 2x plus 1? That's not always an easy question to answer. So as we do some examples here, we're going to discuss strategy. So depending on the integral that we're trying to evaluate, choosing what u should be will vary a little bit from here to there. And we'll discuss some strategy on how to determine that. All right, so when you're looking at a calculus book, right, usually the calculus book starts off with kind of a general rule. And here's how most calculus books write the substitution rule. They usually say, well, something like this. They'll say, if I'm taking the integral of f composed with g of x, f composed with g of x times g prime of x, we can write this as the integral of f of u du. And so what we're really doing here, if you notice, we're taking the u variable and we're substituting it for the g of x. So what I've done, my change of variable was to let u equal g of x. And then the derivative, if I do that, is, g prime. So my du is g prime of x times dx. So this guy, g prime of x, is the du. G prime of x is the du. So this is the general statement of a U-substitution or a substitution rule. And if we point out to ourselves just a moment, what we're really seeing here is a composition. So notice what we did with our substitution is we let u be the inside of this composition. When I let u be the inside of this composition, it will simplify the integral for us. So when we discuss strategy, as we continue to move through these problems, what we're typically going to do is we're going to look for the composition within the integral. We're going to let u be the inside of that composition, and that will 98% of the time accomplish the substitution working for us. One or two exceptions to that strategy, and we'll discuss really what those are when we look at some examples. All right, and then the other thing I want to point out to you that we're going to look at as part of our strategy is when we let u be the inside of this composition, in order for this technique to work, we need the derivative of the inside to be a product of the f function, right? So notice that when I let u equal g, here's its derivative, g prime. If I'm going to let u equal g and I don't have the derivative g prime elsewhere in the integral, this technique won't work. So the substitution rule is kind of unique in the sense that it has to be a composition, and as part of that composition, the inside of the composition, its derivative needs to appear in the rest of the integral, if you will. Now, if we can't match that form, right? If we don't have a composition where its derivative also appears in the integral, then the substitution rule won't work, and we would need another technique of integration, and that would be something we would talk about, in a Calculus 2 course typically, that we'll discuss together, right, later in another video. So all the problems we see in this section will match this particular form. Okay, so let's look at a second example here. So the second example I'm going to look at is, let's say, 2x times the square root of 1 plus x squared dx. Now when I look at this integral, again, we're having a conversation about the substitution rule. So this integral is going to match the things that we need to match. So first of all, we have a composition. So notice right here, I'm going to circle it. Right here we have a composition. Right? What is it we're composing? We're composing the root function and the quadratic, 1 plus x squared. Now notice within that composition, the quote-unquote inside is the quadratic, 1 plus x squared. The outside of the composition is the root function. So usually 98% of the time we're going to let u be the inside of the composition, right? I'm going to scroll back up. Just like we just said, we have a composition. We're typically going to let u be the inside of the composition. So we're going to let u equal 1 plus x squared. Now if this is going to work, the derivative of the inside has to be in the integral, right? That g prime had to be in the integral. Scroll back up a little bit more. And notice that's going to work in this case. If we let u equal this quadratic, its derivative is 2x, and that is in the integral. So this integral is constructed in a very convenient manner so that u substitution will work. Right? So let's go ahead then and attack this problem. So if I have the composition where its derivative appears elsewhere in the integral, right, then we're going to let u be the inside of that composition. So let's take that approach here. Let's let u be the inside. What are you doing? Go away. Let's let u be the inside of that composition. So let me switch to red. So I'm going to let u be the inside of that composition. So I'm going to take some baby steps here just for our conversation. And what we end up with is the square root of u. Now, just like we talked about in that first example, I now have a mismatch of variables, right? I have a u variable and these x variables, and I need to get everything in terms of the u variable. This needs to be a du, this guy needs to be in terms of u, if we can, right? And that's always going to come from the derivative of the u. So I'm going to come back over here, and I'm going to take the derivative of the u function, and that's going to give me 2x. And then there's a couple different ways to attack this, right? Now I'm going to do both ways as we continue doing examples here. But I think probably the more straightforward way is to do what we did in the first example. We're going to take the derivative formula, right, derivative equation, and we're just going to algebraically solve for the dx. So I'm going to multiply the dx to the other side, and then the 2x I'm going to divide over. So let's say I have du over 2x equals the dx term. And I'm going to just substitute. So the dx that I have in my integral, I'm going to replace it with du over 2x. So this is du over 2x. And then I have this 2x still here. I have the square root of u, right? And we're integrating. So here's the way that the u substitution rule works, right? So because my u term, 1 plus x squared, its derivative appeared elsewhere in the integral, then what's going to happen here always is those terms will cancel, right? So the end goal is to completely change the variable of my function, right? So my original integral, right? So I have the square root of u times du, and we've converted all of the x's in my original integral now to the u variable. So we're doing a change of variable. And again, that's why this is called the substitution rule. Now at this point, I'm matching one of my, quote unquote known integrals. I could do this as brute force, right? This is an elementary integral. How do I evaluate the root function? I'm just going to keep everything in red at this point. I write it as an exponent of 1/2, and then I add 1 to the power, multiply by its reciprocal, and I add c. Now the thing that I didn't do in that prior example that I should have done, but I wanted to focus more on the concept. Because my original integral is in terms of x, let me scroll back up a hair here. Right? My original integral that we have up here at the top of the screen was all in terms of x, but my answer is not. My answer is in terms of u. So the last step we really need to do here is replace u with what we substituted. Right? We let u be 1 plus x squared. I've not scrolled enough, right? We let u be 1 plus x squared, and I'm going to replace that back into my antiderivative of my u variable. So my last final answer here would be to say 2/3 my u was 1 plus x squared. And then there is our final answer in terms of the x variable. Excuse me. So again, what I want to do here is, let me see if I can zoom out real quick. I want to kind of look at all of this together. Let's do a review of the whole idea behind U-substitution. So I have an original integral. The original integral does not match one of my known forms. I can't really brute force this. So what I'm going to do is substitution. I'm going to change my variable. Now the only way that this technique can work is, number one, I really need to have a composition, which we had here in green. And then if I let u be the inside of the composition, which is what I'm supposed to do, its derivative is 2x, and it needs to appear elsewhere in the integral. So we set that up. We let u be the inside. We take its derivative, and then we solved for the dx term. We wanted to replace this dx. So I take its derivative, I solve for the dx, I plug that in. The x is canceled here, and my end result of substituting, all the x's are gone, everything's in terms of u. Now, this is now a quote-unquote known integral. We use the power rule. Our answer was in terms of the u variable. We just needed to get it back in terms of the original x variable based on the substitution for this particular example. So this will be the process for all of the problems we're going to continue to do here over the next 10-ish minutes. Right? We're going to have basically a composition, and we're going to substitute, so simplify the radical, simplify the integrand of my integral. Now, as I mentioned, there's a couple exceptions, right? 98% of the time I'm letting u be the inside of the composition. There's a couple exceptions where it's not obvious that that's what I'm doing, and we'll look at a couple examples like that. And what I want to do is I'm going to go back and fix my very first example, and I want to substitute the u to get it back in terms of x. I really didn't complete that correctly. So where was my original integral? Oh, that wasn't it. Here we go. Here was my original integral. Right? So my final real answer here. We had this integral 1 over 2x plus 1. We let u equal 2x plus 1. My answer is in terms of u. I need to get it back in terms of x, right? So here's my integral. Right? This guy equaled this guy, which equaled this guy. So this is 1/2 ln of, and then I plug what my u is. My u was 2x plus 1. And there's my real final answer here. So let's do a couple other examples. So let's take a look at a couple other examples here. So let's say in this example we're going to integrate, let's do the cube root of 2 minus 5x, let's say. All right, now continuing to have the discussion that we've been having up to this point in regards to I need a composition, and I have that in this example. What's the inner function here? Correct. The inner function is 2 minus 5x. What's the outer function? That is correct too. The cube root is the outer function. Now we had said a couple minutes ago that I'm going to let u be the inner function. And what I expect to see is the derivative of that inner function elsewhere in the integral. So if I change to red here and I let u equal 2 minus 5x, right, what's the derivative of 2 minus 5x? It's negative 5. I don't see a negative 5 multiplying outside the composition. Well, in this case that doesn't really matter because the derivative of my inside is just a constant, and I can move a constant around, right? I can move it in and out of a derivative operation. I can move it in and out of an integral operation. So something kind of unique with this u substitution. So if I'm letting u be a linear expression, 2 minus 5x is a linear expression, then the substitution will work quite nicely even though its derivative isn't elsewhere in the integral, right? So for example, we really saw this in our very first example. If I solve for the du term here and then I solve for the dx term, what would I have? I would divide the negative 5 over, and there's my dx. Right? So I'm going to have cube root of u when I substitute for the inside, and then the dx expression is right here, negative 1/5 du. My fingers don't always want to work. I'm negative 1/5 du. So again, when the inside is linear, its derivative is constant. And this constant of negative 1/5, I'm just going to pull out front of the integral. And there's our change of variable. Man, that is a sloppy u. Right? Okay, so there's not necessarily an exception to the letting u be the inside, its derivative needs to be elsewhere in this example. It just doesn't look obvious that the derivative being constant can be moved around without any issue. And if I scroll back up for a moment, I paused it real quick so I could scroll. If I scroll back up to that that first example that we talked through, notice when I let u be the denominator, right? U being the linear expression, 2x plus 1. The derivative of 2x plus 1 is just a constant of 2. And so I was able to, move the constant over to make it a 1/2. And then that 1/2 that we had here, I just pulled out of the integral. So whenever I'm letting u be a linear expression, the u sub will work for the most part, right? And when we're working with problems in a section where we've learned about the u substitution rule. So we're seeing that same type of thing work here, letting u be the linear inside the composition, the constant of negative 5, the derivative of negative 5, I just pull over as a negative 1/5 and that pulls out. So we may see that happen again as we continue to work on some examples here. So just to finish this example, go back to red. So I have u to the 1/3, so I'm going to add 1 to the power. So let's see, what's negative 1, excuse me, what's 1/3 plus 1? I'm usually going to talk myself through this mentally, right? But, or I should just say verbally. 1/3 plus 1 is 1/3 plus 3/3. So I don't really want to have to say 1/3 plus 1 is 1 1/3. I just can easily write the number 1 in terms of whatever this denominator is, right? 1 is going to be 3/3. If this was 1/10, I would write the number 1 as 10 over 10. So it makes it pretty easy to add if we just think that way. So this is really just 4/3 when I add together, and then I multiply by the reciprocal. And then you always tack on a plus c here. Did I do that on the prior problem? Uh-oh. I can't remember if I tacked on the plus c there. So then this final answer, I'm going to substitute in for the u, and our u was 2 minus 5x. Right? So my final answer here, I'm running out of room. So the u being 2 minus 5x. So I'm going to say 2 minus 5x to the 4/3 power plus c, and then I have, what do I have here? I have negative 3/20 as the coefficient. So there's my antiderivative of my original integral by doing a U-substitution, changing the variable, so we could just use a simple power rule here. All right, I want you to try one for me. So I'm going to write this integral on the board. Let's say we have integral of e to the, let's say, 5x dx. So this will work with U-substitution. I want you to pause the video. I want you to try this on your own. And then when you're done, unpause and we'll do this together. All right, so how did you do? Let's check and see how you did. All right, so when I look at this integral, remember I'm looking for a composition. So what's the inside of the composition here? That is correct. It's the inside of the exponential, right? It's the exponent. And then what's the outside of this composition? That is correct. It is the exponential, the base e. So I'm going to let u be the inside of that composition. And then we're seeing the process will always be finding the derivative of our u. So that's 5. So then I'm going to multiply the dx to the other side. And then I'm going to get dx by itself. And so I'm going to substitute that expression. Right? So my u is 5x. So I have e to the u. And then my dx is 1/5 du. And so there's my simplified integral. I'm going to pull the constant outside. All right, and then what's the integral of e to the u? Well, again, we know, let me switch to green real quick, right? We know that the integral of e to the x is e to the x. So that's really what we have here. E to the u du will be e to the u. So I really have 1/5 e to the u plus c. And then I'm going to plug back in what my u is as 5x. So I have 1/5 the integral of 5x plus c. And there is the antiderivative, right? There's the integral we were originally given, right? Evaluated. Now, again, notice all these examples I've been doing indefinite integrals. I haven't put limits of integration on anything because what I've wanted to focus on is the method of the antiderivative. Obviously, if I had limits of integration here, I would plug in the limits of integration on this last step. I want to do an example like that in just a moment. But just wanted to point out to you, right, I've been wanting to focus on the technique here. Okay, let's do a couple more together here. So this one's a little bit different in regards to the composition is not obvious at all. So I want to work on this one with you together, right? Just so we can see where the composition is really occurring. This is kind of weird. So I'm going to integrate tangent of x. Now initially when we look at tangent as such a simple integral, we think to ourselves, oh, you know, this has got to be one of our known integrals. And it is not. If we were to scroll back up to our table, we wouldn't see the integral of tangent equaling anything. We don't have the integral of tangent. And you know, the reason why is we're asking the antiderivative of tangent, right? What do I take the derivative of to get tangent? And there is nothing that answers that question. So technically, to evaluate this integral, what I need to do is I need to write tangent as sine x over cosine x. Now, why is that fruitful? Well, this is fruitful because this integral really is, I'm going to write it as 1 over cosine x times sine of x dx. So I'm kind of thinking of, you know, this as a term and this as a term. And this guy right here, this 1 over cosine, is really a composition, right? How is it a composition? Well, the outer function is 1 over x. The inner function is cosine of x. So the inner function is cosine. The outer function is 1 over x, right? So I really have 1 over cosine x. So cosine is the inside of the composition. So remember, if these are supposed to work, the inside of the composition, its derivative should appear elsewhere in the integral, and it does in this case. What's the derivative of cosine? Well, negative sine technically, right? But the derivative of cosine is some sine form, and there is its derivative. So the u sub will actually work quite nicely here. So I really have 1 over u in that expression. And then now we take the derivative of my u variable. Derivative of cosine is negative sine. I'm going to multiply the dx over. And then I'm going to solve for the dx. I'm going to just say du over negative sine of x would be the dx term. So this substitutes the dx, right? My dx term. What is my dx term? My dx term is du over negative sine. I'm just going to say negative du over sine. Pull the negative up front. We can see the signs cancel here. So I have a negative 1 that I'm going to pull in front as a coefficient. And then the signs cancel, and I get 1 over u du. So I'm going to stop for a second, right? This was an interesting problem in the sense that it was not obvious that this was a composition. So now we can see pulling the tangent apart as sine times 1 over cosine actually worked kind of nice. So let's finish this off then. So the integral of 1 over u, or what's the integral of 1 over u? It is ln of u plus a constant, and then we had let u equal, we'd let u equal cosine. So I have negative ln of cosine of x plus c. Now in a textbook, right, and I'm moving along with the Stewart Calculus textbook here. If we look in the Stewart Calculus textbook, what we actually see is that the integral of tangent is ln of secant. So I'm going to scribble over here in green. We usually see the integral of tangent is ln of secant. So how do we make the connection, right? Our answer was negative ln of cosine. How do we make this guy be ln of secant? All right, so what we're going to do then is use a property of logarithms. So remember, a property of logarithms we have, let me switch back to green. We have like, if we have ln of a to the b power, this exponent I can pull in front of the logarithm. So I'm just going to go backwards. I'm going to take the coefficient and pull it in as an exponent. So my coefficient of negative 1, I'm going to pull in as an exponent. Now, this is not inverse cosine. This is cosine to the power of negative 1, which is really 1 over cosine to the positive 1 power. And then that's where our secant comes from, right? 1 over cosine is really secant. So integral of tangent is ln of secant plus some constant. All right, now just like in the textbook, right, usually the reason we do this integral as an example is what we're going to do is we're going to add this to our quote-unquote known integrals. So what we would really want to do here is go back up to our table and add this in as one of the results. So I'm going to do that real quick. I'm going to scroll up, and I am going to add on to my table that the integral of tan x dx is ln of secant x plus c. So from now on, when we're doing integrals, if I see integral of tangent, I just want to know that's ln of secant. I do not want to have to do u sub to find the answer, if you will, to find the antiderivative of tangent of x. So anytime from now on, if we're integrating tangent x, we're going to jump right to the result of ln of secant. So, the reason we do this type of problem is just to point out to ourselves that it's not always obvious where the composition is. All right. So there may be a couple problems in a homework set that you have where it's not obvious the composition. Sometimes you just got to pull things apart and investigate. Now, something else I want to mention to you is that as we do examples together, as I do problems for you in these videos, I know how to do these problems. I know what I'm going to let you equal. And I'm setting up an unrealistic expectation for your experience in the homework. Something you got to keep in mind is when you're doing these integral problems, it's not always obvious exactly what to do the very first time. So something you have to understand, something you got to think about is when you're doing these U-substitution problems in the homework, sometimes you're going to do the wrong thing. You're going to try the wrong U term, and you're never going to end up eliminating all of the variables here. So one of the ways you know that you did the correct U-sub is when you get to the end, your entire integral cannot have x's in it anymore. If you don't eliminate all the x's, then you need to come back and choose a different expression for u. So sometimes these problems are a little more difficult and you need to explore. Just try something and see what happens. Don't be afraid to try something and get to a point where you can't go forward. Right? Call it a mistake if you will, right? We learn best from our mistakes. So there will be times when you do the homework, you don't choose the proper u. You get to this point here where you did not eliminate all the x's, that indicates you chose the wrong u. So again, keep that in mind. That will sometimes be a part of your learning process in this type of section. Okay, so I'm going to do one more example with you. And I want to look at a problem, an integral, where we're going to have limits of integration. So again, we've been doing all integrals here that were indefinite, no limits of integration. So I'm going to do one more where we have limits of integration. We need to work through that. So the integral we're going to look at, let's say we're going to look at the integral of, let's say, I don't know what to do here. Let's say sine of x, nope. I want sine of, let's say sine of 2x dx, and we're going to go from 0 to pi. So last example here, let's take a look at a definite integral. Right? So an integral where we have limits of integration. So when I look at this, when I'm looking for a composition, the best that I can find, locate, identify a composition here. So the inside, right? What's the inside of my composition? Yes, that is correct. 2x is the inside of the sine function. So the sine function is the outside. 2x is the inside. So let's let u equal 2x. So I'm going to take the derivative of the u term, and that gives me not 2x. That gives me just 2. I'm going to multiply the dx to the other side, and then I'm going to solve for the dx. So then let's plug everything in. So the inside of the sine was our u substitution. And then the dx expression that we have here is the 1/2 du from our derivative. Now for just a moment, I'm going to leave off my limits of integration. I'm going to pull the 1/2 in front. And so what I'm integrating is sine of u du. Now, there's two paths that I can take at this point, and I want to take both paths and discuss the purpose, right, of both paths, and that our answers really would be the same. Now, what I'm going to do first path, is I'm going to do everything we've been doing prior. So in other words, I'm going to evaluate this integral in terms of u and get the answer back in terms of x. So I have my constant out front. What's the antiderivative of sine of u? It's negative cosine of u, plus c technically, right? Now, I'm going to get back in terms of the original x variable. So my u was the expression 2x, let's say plus c, right? And then I'm going to evaluate as x goes from 0 to 2 pi. Right? So I'm going to plug in the 2 pi, I'm plugging the upper limit. So I'm going to have minus 1/2 cosine of 2 times 2 pi. There's my upper limit, and then minus, so the lower limit, minus 1/2 cosine of 0, plus c technically, right? So if I simplify all of this, you know what I did? Hang on, I want to fix this. I should have a plus c right here, right? Technically, when I plug in 2 pi, right? When I plug 2 pi in to here, I'm going to get negative 1/2 cosine of 2 times 2 pi plus c. There's my upper limit, and then minus, with my lower limit, negative 1/2 cosine of 0 plus c, plus c as well. Now, notice what's always going to happen with the c's, right? Like we talked about in 5.3 when we were doing definite integrals. This c subtracts this c, so we're always going to get our constants to cancel. So again, what we typically do when we have limits of integration, we just don't write the constant, right? We ignore the constant because it's going to subtract itself off anyway. So then what do I have in this case? I have cosine of 4 pi. Cosine of 4 pi is positive 1. I have negative half times positive 1, and then minus, and then I get cosine of 0. That is also positive 1, so I get negative 1/2. I have minus negative 1/2. So I really get negative 1/2 plus 1/2, which is 0. Now, let's show ourselves that the other path I'm going to take produces the same answer. So let me zoom out a little bit so I can kind of see the same thing here. Now, come back up to our original problem. I have to scroll back down in just a second. But when we did our change of variable, we had x variables in our very original integral. We made a substitution, and we got our integral all in terms of u. Now, it would be a mistake to say 0 to pi on this integral. And the reason why is because the 0 is a limit on x. Pi is a limit on x. Those are not u limits. So what I could do at this point, let me change color, I could come back to this problem and I could pick u limits. So I could have 1/2 the integral sine of u du. So how do I find the u limits? Well, actually pretty straightforward. It comes back to my substitution. If x is 0, my bottom limit, right, my lower limit, if x is 0, I'm going to plug 0 into the x, and u would be 2 times 0, which is 0. If my upper limit is x equals pi, I'm going to take pi, plug it into my x, and u would equal 2 times pi. So we can see that the limits on the u variable are 0 to 2 pi, when the limits on the x variable were 0 to pi. So we would have an error if down here we had written 0 to pi as our limits of integration, because that is not correct. So this is kind of the other path we can take. When we do a u substitution, we can convert the x limits of integration to u limits of integration. Now let me separate all of this with a little squiggly so we can do this work separately. Go back to green. Right, so what is the antiderivative of sine of u? That is negative cosine of u. We technically already did that. And what we're going to do at this point is not go back to the x variable. Right? The reason we're not going to go back to the x variable is we converted our limits of integration to u limits. So I'm going to take these limits on u and plug them into my u function. So I'm going to have negative 1/2 cosine of 2 pi, and then I'm running out of digital paper. Here's me plugging in the upper limits. I'm going to subtract with the lower limits plugged in. Okay. Now, what are we going to get out of this number? Let's see. Cosine of 2 pi is positive 1, so I get negative 1/2. And then minus cosine of 0 is 1 times negative 1/2. So I get negative 1/2 plus 1/2, which is 0. And of course, we should get the exact same answer that we got over here. It was the same integral. So two different paths you can take, right? Which one do you want to take? It's up to you. It's personal preference. If you want to go ahead and do the whole problem, getting answers back in terms of x, using x limits, by all means do that. And if you want to leave the limits of integration, convert to u limits, then we can do that as well. You know, and I think I'm noticing a mistake here. Did you guys catch my mistake? Hang on a second. I have x limits of integration of 0 to 2 pi, and I have u limits of integration from 0 to 2 pi. So where did I make a mistake here? Aha! So here was my mistake. My original x limits of integration was 0 to pi. And I think I must have been looking ahead. And let me fix this. Let me take out my eraser. And this would be 0 to pi. Those were my x limits of integration, 0 to pi. So what does that change? Let's see. Instead of plugging in 2 pi over here, I'm plugging in pi, erase. I'm plugging in just pi. And then, so this is cosine of 2 pi, which is positive 1. So I positive 1 times negative a half, and I end up with the same thing here. All right, so just wanted to fix that. I noticed my x limits were the same as my u limits, and that's not true. So two different paths we can take when we have a definite integral with limits of integration, and we're having to do the antiderivative by substituting. We can get the original variable back into our antiderivative using those limits of integration, or we can convert to u limits of integration based on what we substituted. All right, so I think that's everything that I want to do in this video. Really, everything up to this point, we've discussed integrals, measuring area. We've looked at kind of the bigger picture in regards to that, right? That's one of our applications of integrals. And then when we get to this section, we consider integrals, right, of functions that aren't elementary, aren't standard antiderivatives. And so we have to use a technique we call substitution. We replace the variable to simplify the integral into a form that we then can do the antiderivative as a known elementary function. All right, I'll see you in the next video.